Good morning, everyone. So today we are going to learn about setting reaction of GIC. Setting reaction of GIC can be explained by dividing the whole process into four stages. We all know GIC consists of a powder as well as a liquid component. Powder as a whole, we can say it as calcium aluminofluorosilicate glass particles, and liquid, we have a combination of polyacrylic acid along with other polymers like tartaric acid, itaconic acid, malic acid, and even trace amounts of water. So by setting reaction, what we are basically going to learn is what happens when the powder is mixed with liquid. The powder, which is basically glass particles, when it is mixed with liquid, which is polyacrylic acid, what is the reaction that takes place? The first stage in setting reaction of GIC is called stage of dissolution. That is, when the powder and the liquid are mixed together using an agate spatula on a paper pad, the acid, that is polyacrylic acid, will attack the outer layer of the powder particles, which are basically glass. And when this attack happens, ions like calcium, aluminum, sodium, silica, and fluoride ions will be released into the aqueous medium. So this is basically the first major step during the setting reaction of GIC. The powder and the liquid are mixed. The acid from the liquid will attack the powder particle, resulting in release of all these ions into an aqueous medium. Next, we have stage 2, which is the initial setting. And the initial setting of GIC takes place through calcium cross-linking. The initial clinical set is due to the cross-linking of calcium ions with the polyacrylic acid. The calcium ions are released from the powder particle. They will interact with the polyacrylic acid liquid, displace the H plus ions from the acid, and they will form a bond. The calcium ions will form a bond with the polyacrylic acid, and this process will continue up to 3 hours. Calcium ions are doubly charged and ionically bonded to glass particles, and hence they're they're readily liberated by ion exchange of H plus ions of the acids. Calcium ions are just ionically bonded to glass particles, and hence it is easier for the H plus ions to displace it. So in exchange of H plus ions, the calcium ions will interact with the polyacrylic acid and form a calcium polyacrylate salt. So the initial clinical set, that is for 4 to 10 minutes, is a time wherein the material is carvable. So if you place GIC into the cavity, the first 4 to 10 minutes when the initial setting is happening, you can actually slightly manipulate with the material, uh, and there will not be hard enough to resist sharp instruments. So mild manipulation can be done during this stage. Here you can see calcium ions displacing the H plus ions, and they will react with the polyacrylic acid to form calcium polyacrylate salt. This brings us to the stage 3, which is the final setting reaction. The final setting reaction can also be mentioned as gelation, and the final set mainly happens because of aluminum cross-linking. Gelation, or the final set, occurs during the next 24 to 48 hours when the less mobile aluminum ions cross-link with the polyacrylic acid chains. As I've mentioned in the first slide, calcium ions are readily displaced because they are just ionically bonded to the powder particles. But aluminum, on the other hand, it is covalently bonded to the glass particles, and they can only be liberated by slower hydrolysis. That's why the final set or the gelation happens 24 to 48 hours after you start mixing the powder and the liquid. So aluminum is covalently bonded to glass, and can only be liberated by slower hydrolysis. Aluminum ions are less mobile and hence they are released much later. So there are two reasons why we have a delayed final setting reaction. One is the final setting happens because of the release of aluminum ions. The aluminum ions are released at a much later stage because aluminum is covalently bonded to glass particles and they can be liberated only by a slower hydrolysis. Aluminum ions are less mobile and are released much later. So this aluminum ions, just like calcium ions, they will chelate with the carboxylic group. And this aluminum ions will even displace the calcium ions, which was previously bonded to the polyalkylic salt because of its higher charge and stronger bonding. So here you can see aluminum ions after 24 to 48 hours, they will be released by slower hydrolysis. They will react with polyalkylic acid and form aluminum polyalkylate salt. Here you can see the positive charge on the complex aluminum polyacrylate complex because of the greater strength of the aluminum polyacrylate bond. And this aluminum will displace even calcium from the calcium polyacrylate salt and eventually result in formation of aluminum polyacrylate salt. So the final set is because of the formation of aluminum polyacrylate salt along with calcium ions which will be released. Now, if you remember, in the first initial stage, a lot of ions were released, not only aluminum and calcium. Along with aluminum and calcium, there was a release of fluoride ions, sodium ions, and even silicate ions. So, where did they go? The sodium and the fluoride ions actually do not participate in the cross-linking of the cement. Sodium ions may replace hydrogen ions in the carboxylic group, but they do not take part in the actual cross-linking. Remaining ions, that is the remaining sodium ions along with the fluoride ions, they will be dispersed uniformly in the set cement. But they definitely have a purpose, which we'll discuss in the coming slide. Now, as hydrolysis continues, more amount of aluminum and silicate ions are released, and these silicate ions will react with H plus ions which are present on the surface of unreacted glass particles to form an important structure which is called silica gel sheath. Now, in the first step, a lot of ions were released, and all the H plus ions will not take part in the reaction. Some of the H plus ions will be present on the surface of unreacted glass particle. So the silicate ions which are released in the first step, they will react with H plus ions, and they form an important structure called silica gel sheath. Excuse me, which can be written by the formula SiO2.2H2O. Now that brings us to a final stage of setting reaction of GIC, which is stage 4, hydration and maturation of said cement. Now we have calcium and aluminum polyacrylate cross-linked matrix. They become hydrated over time with water being present in the liquid. So every component in the powder and liquid has its own significant role. We have learned that in the liquid component of GIC, we have quite amount of water. Now, what is the role of water? The final aluminum and calcium cross-linked matrix, they become hydrated over time. The strength increases over time because of the presence of water in the liquid. So, what is the basic role of water in the setting reaction of GIC? 11 to 24% of the set cement has actually water. Initially, this is very important from a viva point of view as well as from a theoretical point of view, as well as from a clinical point of view. Initially, water serves as a reaction medium. So it provides a medium where the cross-linking between calcium polyacrylate and aluminum polyacrylate can take place. And then eventually, water helps in hydrating the calcium and aluminum cross-linked matrix, thereby helping in increasing the strength of the set cement. That at this juncture, let's learn about what is loosely bound water and tightly bound water. Now, during the initial setting, water is just loosely bound to the whole structure and they can be easily removed by desiccation. So if water is easily removed by drying during the initial setting process, then water acts as a reaction medium. And if water is completely removed, this loosely bound water is removed, then further setting reaction will not take place. Now, any contamination of water, excessive water uptake, can also result in dissolution of the matrix, releasing calcium ions from the polyacrylic chain. So excess water should not enter the cement during a setting reaction because excess water can cause dissolution of the matrix, releasing calcium ions from the polyacrylic chains. So, important thing to note is that both loss as well as uptake of unbound water can make the cement more weak, soluble, and having reduced translucency. The role of water in setting reaction of GAC is very crucial. Both loosely bound water and tightly bound water. And what is the role of water in GIC? Initially, it serves as a reaction medium. Later on, it will hydrate the matrix and increase the strength. So to prevent the loss of unbound water, immediately after placing GIC onto the cavity, you can apply a coat of varnish or a Vaseline on top of the ODA cavity. All right. Now, whenever you're learning or writing about setting reaction of any cement or material, you should mention about the structure of the set cement. What is the final product that we receive? The set material consists of unreacted glass particle surrounded by silica gel sheet embedded in a polysalt matrix cross-linked by ionic bridges. We have a unreacted glass particle surrounded by silica gel sheet in a cross-linked polysalt matrix, which are linked by ionic bridges. That is the structure of the set cement. Now you may be wondering, what is the role of fluoride ions? Fluoride ions, which are released from the glass, will lie freely within the matrix and can move freely in and out of the set cement. So what is its significance? All of us know fluoride has anti-carcinogenic property. So the surrounding areas around the cavity rusted with GIC, that area the will have abundant of fluoride. This GIC will act as a fluoride reservoir. Whenever there is an ionic imbalance, whenever the surrounding area has more demineralization, the fluoride from the GIC will go to that area, supply fluoride, and promote remineralization. And by exchange of fluoride, the GIC will act as a fluoride reservoir, and that is the main role of fluoride. So every component in the powder and liquid has a very significant role in GIC. Thank you so much.